So hello Math 2 students, this is lesson 134. And so we're going to be talking about three different conjectures in this lesson, different ideas. And the first one is the easiest of all, and it's called the Pi Triangle Sum Theorem. And so you may already know that the angles in a triangle add up to 180, and today we're going to prove it. So if a polygon is in a triangle, then the measure of its angles add up to 180. That's our 180 degrees. So that's our conjecture. We could rephrase the second part. Then the sum of the angle measures is 180, which is what I would have written, but this one's fine. So that's our proof. We're going to use this picture to help us and a couple of other tools. So one thing to just kind of keep in mind, this picture came from a zooming in of Marcos's tiling pattern. So we've talked about Marcos a couple of times, and so he's taken his tiling pattern and drawn some diagonals on it, and so we're zooming into a portion of that. I didn't find this picture very, very helpful. It is from your textbook, and I thought we should bring it up in case some of you like it. But it basically reinforces that what we have going on here is parallel lines cut by two transversals at the same time, and so that can be a little bit frustrating and overwhelming, but that's really what's happening. We're going to actually spend some time with the triangle sum theorem here on Desmos, this e-tool, which I found to be exceedingly helpful. So here's the tool. You'll notice I have a bunch of angles, and if I scroll down, I can see 180 is the sum, and then I've got these angle numbers, and if I drag A, I change the number. See how the numbers are changing as I move A around? I can also move B around. The numbers change there too. I can move C around, the numbers change. And so, but you'll notice the sum stays the same the whole time. So what I want you to do is see if you can come up with one where the sum isn't 180. So play and see if you can make one not 180. So use the e-tool, which you can find this particular e-tool in our assignment title on Google Classroom, and then you can click on it and play games. But the idea here is pretty basic. If we turn on parallel lines, though, we can find something else more interesting. And so I'm going to go ahead and kind of leave it in this goofy obtuse shape. I find it more helpful. And so I'm going to go ahead and get this going. And so if this is my transversal, so just focusing on angle B here, which is blue, then this angle right here is the same as angle B right there because they're alternate interior angles. And if I let this be my transversal, what a terrible drawing, this be my transversal, then these two angles, this one and this one, are the same, again, because of alternate interior angles. And since this green angle and that blue angle match these two, which are in the triangles, and A is already there, these three angles make a line. And what's the sum of the line? Well, the sum of the line is 180. And that's the idea behind our proof, okay? So we've already kind of started. So, but that's how you kind of use this tool. Play around with it, see if you can come up with something that isn't true. So we're going to go ahead and just focus again on trying to prove this. So we've got this, we've got this. So what I'm going to start with is, we're going to name these lines. Let's call this one L and this one M. And so lines, so I'm just going to say L is parallel to M, and that I was told that right away. It's marked in the drawing. Those are parallel lines. I'm not even really going to say why I know that. It's just obvious that I know that. And so angle A and angle D are alternate interior angles. And angle C and angle E are alternate interior angles. Okay, so that's what I got. And so I'm going to go ahead and mark the C and E with green. And you can see this green side, if I make that the transversal, it's pretty obvious that those are alternate interior angles. Mark the other two with blue. And if this is my transversal, you can see that those are alternate interior angles. Okay, so there's my picture so far. Since they're alternate interior angles, angle A is congruent to angle D. and angle C is congruent to angle E because they're alternate interior angles. And we proved that the other day, actually today. So that because they're alternate interior angles, these angles are congruent. Neat. Okay, so what do we know? The next thing I know is that angle D, angle B, and angle E form a line. Okay, which means that the measure of angle D plus the measure of angle B plus the measure of angle E equals 180 because they make a line. Okay, and continuing, I can then replace D with A. So A comes in for D. Angle B is the angle in the is not being replaced. I should really make it black. Not being replaced. And then angle E is going to get replaced with C, and I'm going to use green. And this one should have been blue. Okay, so that's replacing that. This is replacing that, and I'm finished. That's it. Since these two are congruent, I can replace them, and these two are congruent, I can replace them, and B's there, and then I've got my three angles in my triangle, and all done. That's pretty straightforward and easy. Yay. So go ahead and take a minute and write all that down. And we're going to move on. All right, the next one we're going to be discussing is the triangle inequality conjecture. And this is a little bit different. Now that you've proven the triangle sum theorem, you can always determine the third angle measure of a triangle if you know the measures of the other two. Is there something we can do with sides? And we know the Pythagorean theorem is cool, but that only works when we have a right angle, and B could be some other angle, right? So what do we know anything about the length of the third side? Jenny says it could be anything, and Mary says that's not true. She doesn't think it could be 100. And so who's correct? So what we're going to do is we're going to go ahead and look at this triangle inequality tool and see if we can use that to help us. And again, you can find a link for that inequality tool in our classroom pages. So I'm going to go ahead and set, we're going to make this one the one we don't know. And so we will go ahead and just to move it up, I'm going to put some more things in. We're going to make this one, force it to be 6, and force this one to be 8. Now, they have this one set at 15. Can we make a triangle? In other words, can I drag the B's together? And no, see how they're not quite, there's not enough space for them to actually touch. Let me make that more obvious. I'm going to make this 20. So when I try to get them close together, these two side lengths don't stretch to meet each other because AC is too long. Does that make sense? So AC is too long. Is there a time where an AC could be too short? Let's see. What if it's just 10? Let's try 10. Well, not 110. 10. So can I make these meet now? That is 10. And while I'm having some trouble making it happen, it looks like it should happen no problem. Like they're close enough. If I wiggle it enough, I should make it them the same, right? Okay. So when it was 10, it worked. What if it's 3? Can I make it work? Not really. What if it's 12? And so the idea here is for you to make some numbers up and see if you can figure out what's happening. There is this very specific relationship that has to be true between the longest side and the two shorter sides, or between the third side and the two other sides. So if AC is the longest, it has to be what? So 6 plus 8 is what? Well, it's 14. And when this was 15, it just didn't quite work, if you recall. It just didn't quite work. They were really close. When I pulled them here onto the line, they didn't meet. And if A is 14, you'll notice that they actually meet. They bump into each other because it's equal, that they're equal. And that's not a triangle either. But if A is 13, if I pull them on the line, they overlap each other. And if they overlap, then they should be able to meet up here somewhere. Okay, does that make sense? And so that's the idea here. And then, is there a place where they're too short? And that would be if AC is not the longest side, and that would make BC the longest side, which means something smaller than 8. So like if it was, say, 7, can we make a triangle? Answer ought to be yes. And so that's the idea. And so the triangle inequality theorem basically says the following. Well, let's see if we can play some games. So leaving this tool open to maybe help you with some of the other questions I'm going to ask. Do you have a conjecture yet? And if the answer is no, that's cool. So Jenny is wrong and Mary is correct, but do we still have an idea? We're going to be justifying. You want to put some sketches in your notes so you remember what's going on with that, when it didn't work, when it did, all that good stuff. But let's take a look at some specific problems. So you can try without a tool, but do you think it would work? So 3, 5, 3, and 10. Do you think that would make a line, a triangle, or not? And think about what happened with our third side when it was too long, and see if you can come up with it. So I'm going to go ahead and see what you can do. If you need to use the tool to help you, go for it. And I'm going to see what you come up with. Go ahead and pause the video now and see what you got. Okay, so the first one did not work. The next one does work, and 3 works, and 4 does not. Here's my summary. The sum of the 2 shorter sides must be greater than the third side. And the truth is that it's the sum of any 2 sides. It does not have to be the 2 short sides. The sum of any 2 sides must be greater than the third side. So 5 plus 3 is not bigger than 10. And 3 plus 10, but 3 plus 10 is bigger than 5. But we have to, it doesn't matter which sides we pick, it should work out. Okay? And so 4 plus 12, well, actually 4 plus 9 is 13, and 13 is bigger than 12, so that one works. I use the 2 short sides to tell. 2 plus 4 is 6. 6 is bigger than 5. 3 plus 5 is 8, so they're equal, so that's not going to work. So, but let's talk about the generalization. What's the generalization going to be? So A plus B needs to be greater than C. Okay? Which means that C, and it has to be, if say B was the biggest, let's say B was the biggest, then we would say A plus C has to be bigger than B, which means C has to be bigger than B minus A. So B being the middle side length, if you will. And so C is stuck in between 2 values. It has to be bigger than B minus A, the absolute value, we'll put that one on there, and greater and less than A plus B. And again, everything's going to be positive, but this one, if I choose wrong, could go the other way. So B minus A with B being, so let's just take the absolute value off that, as long as B is greater than A. Okay, so we're going to make that assumption, and then we can say this. B minus A is, so it's in between these 2 numbers. So if I know 2 numbers, the third side, so if I know 2 numbers, 11, one side is 11, the other is 12, then what's my third side have to be? Well, it has to be some number smaller than 23, but bigger than 1. Okay, and then it'll work. So that's the idea. So if these are my 2 sides, my third side is smaller than 23, which is them added together, and bigger than 1, which is them subtracted. And that's it. Okay, so that's our new thing. So go ahead and take a minute, write that down so that you remember what it is, and we'll be back. Okay, so the last one is a little bit longest side, longest angle. And so when we play with the angles, well, we should notice that something is that's true all the time. So thinking about the Pythagorean theorem for just a minute, the third side, the longest side is the hypotenuse, which is always opposite 90. And so it's always the biggest. The other 90 is the other angle. The other two angles are acute every single time. They have to be because they have to add up to 90 together. And then because of the triangle sum theorem, they have to add up. Those two angles have to be complementary at the right angle. The other two angles are complementary. That gets a little bit tricky. But anyway, it's just to make one of the angles much larger than the other two if one side is really long. And so what we notice here is that the largest angle is opposite the largest side, and the smallest angle is opposite the smallest side, if you see right here. So B is opposite 9, 21 is, so we can see the smallest angle is opposite the smallest side, and so middle angle is opposite the middle side. That relationship, do you think that's always true? And so we can use our previous triangles to play games, but there's another tool, and so that again is also connected in your classroom. And so this is the similarity tool. So we have these triangles. And so what happens is, what we're trying to do is, if we play with this, see how this is the biggest angle in small sides. And so see, this one ends up being the longest. And whereas if I make that, and that's how it has to happen. And so we're not really worried about these ones staying similar or anything like that. So that's what this is really designed for. We're playing and saying, hey, is this always true? So you just want to make a bunch of different triangles and see if this is always true, that the smallest angle, see how these are really close together, and see how these two numbers are really close together, but the slightly shorter side is opposite the slightly smaller angle. Okay, and so that idea is really important. And is it always true? And so that's the kind of game you're playing right now, is that true? It is, because, the constraints of the situation make it so. And see how my angle of 13 is opposite my much shortest side here. And so that's the relationship we're finding. And it can be a little tricky, but that idea. So which angle has the largest measure? So this is a little bit funky, but we need to draw a picture. So we got a side length of 12, that's A and C, and this is 12, and B, and you might want to use the other tool where we can change the numbers by typing them in. BC is 9, and AC is 4. AB is 4, and so will that work? So we want to look at this tool, not this one, but this one where I can change the numbers. So AC was 12. What were the numbers again? AC, wow. AC 12, BC 9, AB 4. B4, BC 9. And so when I make these meet, you can see that the angle B will be an obtuse angle, where the other two angles are quite acute, and C has to be the skinniest. Okay, C has to be the skinniest, because otherwise they won't meet in a reasonable way. Does that make sense? And so that's the idea here with our triangles and what's happening. Okay, and so that makes B the largest angle, C is the smallest angle because it's opposite A, and so on. But the picture really helps to make sure you know which angle goes with which side. I get really confused. And then if we have these angles, which side has the largest measure? The smallest. And since AB and BC are the same, the angles ought to be the same too. And so that's really helpful information. So go ahead and try D with your tool, and that's it for our lesson today, is what's happening with these angles. So good luck. This last one is not as critical as the others, which is why I'm not formalizing it anywhere. But that is the end of our work. So have a great day. I'll see you guys.